Okay, example 1. A parallel beam of light from a laser with a wavelength of 638 nanometers. So our wavelength is 638 times 10 to the minus 9th meters. Now, visible light, by the way, is from 400 to about 700 nanometers. Okay, let's see. Falls on two very narrow slits that are 0.0550 millimeters apart, right? So D is 0.0550 times 10 to the minus 3rd meters, right? So if you see nano just means 10 to the minus 9th. Milli means 10 to the minus 3rd, right? There's all kinds of other prefixes, and they are in your data packet, right? So let's solve A. Okay. What angle set, wait, how far apart are the fringes on the center of the screen? 4.3 meters away. Let's do it two ways. Let's use the quick and dirty formula, and then let's use trigonometry, okay? So let's use the small angle approximation, right? And we'll see if it's warranted, right? Okay, so S is lambda D over D. Okay, lambda is 638 nanometers, so times 10 to the minus 9th, right? The distance that the screen is away is 4.3, right? And then the slit separation is 0.0550 times 10 to the minus 3rd. So let's just try this. Try a little math. We'll do our maths here. So 638 e minus 9 times 4.3 divided by 0.055 e to the minus 3. And I'm getting that S is equal to 0.04988 meters, which with 3 sig figs we'd say it's about 0.499 meters. And I think we did have 3 sig figs. So that's using this approximation, okay? Let's pretend that we have to use actual trigonometry, right? We're not going to use the approximation, we'll use trigonometry. So remember that number, you've got it written down. Okay, I'm going to erase the screen here, right? Okay, so let's do this guy. So n lambda, we'll make n 1 because that'll be the difference between the center and the middle, right? Is equal to d sine theta. So we can figure out theta from this, right? So 1, because it's what distance separates the fringes, right? So we will just go from one to another. So we'll put 1 in there. The wavelength is 638 times 10 to the minus 9th, right? And then that equals 0.0550 times 10 to the minus 3rd sine theta. And I've got my calculator in degrees, so when I do the inverse sine, I'm going to get degrees here. Okay, all right, here we go. So the inverse sine of 638 e minus 9 times 1, don't forget to multiply by 1, divided by 0.055 e minus 3. And that's very small. The angle is 0.6646 degrees, right? Okay, now we got to figure out that distance on the screen, so we got to do a little math here, right? So there's, this distance is 4.3, right? And we're trying to figure out this distance here, right? And whoa, it's so hard to draw. And that angle is, obviously I've exaggerated the angle. That angle is 0.6646 degrees, right? Okay, this is the opposite side, that's the adjacent side, right? So tan theta is opposite over adjacent, so the opposite side is the adjacent side tan theta, right? So the opposite side is the thing we're looking for, right? This is our opposite side of that angle, right? So the opposite, which is what we're looking for, right, is 4.3 tan 0.6646 degrees, right? Again, I'm in degrees, so I'm going to go 4.3 tan. I'm going to grab the number in my calculator. I didn't round it. And I get, doing all of, all this math, all this rigmarole, eschewing the easy formula, I get exactly the same answer, 0.04988. And then I do get some other numbers, like at this point it's different, right? So presumably that's more accurate, right? But you know, in one part in 10,000, that's not bad, right? Okay, so the answer is that it's 4.99 centimeters is the distance separating those bright spots on the screen. So that's part A, right? We just did part A. Let's do part B here. What angle separates the central fringe and the fifth order fringe? What distance is this on the screen? Okay, we can figure out the angle. Let's do this. We definitely need the angle, so we'll do this. Okay, now it's the fifth order fringe, right? Oh, there we go. So we get to put a number in there, right? So 5 is the order, right? The wavelength is 638. Okay, times 10 to the minus 9th, right? And then that equals d. This is our d, right? 0.0550 sine of the angle. So let's figure out that angle, okay? Okay, so here we go. I'm going to do the inverse sine, so second sine of 5 times 638 e minus 9 divided by, oh, that's millimeters, so times 10 to the minus 3, right? Divided by 0.055 e minus 3, whoops, I just did 6. I don't think that'll matter. All right, are we ready for this? Patumba. I get 3 point that the angle is 3.32502 something degrees. So that's the angle. We've answered that question, right? 3.33 degrees, right? How far apart is it on the screen? Let's do the trig. Let's do the trig way first, okay? So this is 4.3 meters, and we're trying to figure out this distance here, right? Whoa. And that angle now is 3 degrees, a respectable angle, right? 3.33 degrees. And again, we're just going to go opposite side is the adjacent side, which is 4.3 times the tangent of 3.32502 degrees, right? So 4.3 tan, that number is 0.2498. Meters, which is about 0.250 meters. Now, let's imagine that we were in a hurry and we just wanted to use this formula, right? Could we just put a 5 in front of there? Let's try it. Let's try it. Okay, so S is equal to 5 times 638 e minus 9, right, times 4.3, all divided by 0.055 e minus 3. So when I say e like that, I'm just, that's calculator notation, right? Okay, let's try this. 5 times 638 e minus 9 times 4.3 divided by 0.055 e minus 3, and I get 0.2494. Right, so it's a little bit off, right? We're just a little bit off, but not much. With 2 sig figs, we'd be okay. With 3 sig figs, we'd say 0.249, and we couldn't quite round up. Okay, so am I worried about that? Not too much, okay? But you know, 3 degrees is a little bit too much angle to use this for, okay? Just saying that, okay? And then let's do C here. This is B, right? Let's do C. What distance separates the central fringe and the first minimum destructive location, right? Well, that's the distance from here to here, right? And that, of course, will be a half a wavelength, right? So to get the destructive interference, you're going to go n plus 1/2 lambda, right? And n could be, in this case, it'll be 0, right? Okay. So I'm going to go 1/2 lambda as d sine theta, right? Could I just do a half there? I bet I could. Let's do that. So should I do it both ways? No, I don't know. I'm going to do it this way. I'm going to do this guy. I'm going to go S is 1/2, because we know that it's going to work for half a wavelength, right? A half 638. I'm using this guy here, right? So instead of a whole wavelength, a half a wavelength. Half 638 e minus 9, right? Times d, which is 4.3. divided by 0.055 e minus 3. All right, 0.5 times 638 e minus 9 times 4.3 divided by 0.055, e minus 3, and I get 0.02494 meters. With 3 sig figs, we'd say 0.0249 meters. Ta-da. All right, quite an example. It's got everything. There it is. All right, so if the angles are small, that is, if the screen is 5 meters away and these things are a few centimeters apart, feel free to use this one. If you start getting angles, certainly about 5 degrees, then steer away from that one. Use this one, and then tan, right? What is tan? Tan is, I guess what? Tan theta is equal to S over D, right? Opposite over adjacent. So here's your D right here, right? Is the distance to the screen, big D, right? And then S is there, right? Yeah. Anyway, that's not in the data packet, but that's just obvious. So.